thank you all for coming here. And thanks hugely to Klaus and Rode and Schwarz for having invited me here. I'm Björn Fahller. I live in Stockholm in Sweden, where I work primarily with developing software for networking equipment. I will not bore you with that. Stockholm is a place you would feel right at home with, because we have that. This is a brewery that was founded in the mid-1800s, and it closed down in 1971, I think, I'm not sure. It's currently a concert and conference venue, primarily. There are some offices. So if you want to live in Munich, in Stockholm, you know where to go. More function more. I did a talk about this topic in 2018, and the reason I decided to write that talk was that I had written a few higher order functions, and my colleagues accused me of witchcraft. And I figured, no, that is not fair. This is not magic. This is maybe a bit unfamiliar, but it's not super weird. We'll see if you will also accuse me of witchcraft after this presentation. Forgot to start my timer, of course. Anyway, the reason for doing this now, though, instead of the 2018 talk, I liked the 2018 talk. It was good, but a few years have passed. The core language has evolved. We have new features in the language that make things easier, more expressive. The standard library has evolved tremendously. We have so many more things that are easier to use and fit better with higher order functions. And my experience is that most of you C++ developers aren't really used to thinking about higher order functions, and I hope to change that today. And also, I have changed since 2018. I've learned things. I've gained new insights. And that is also worth talking a little bit about. As Klaus said in the introduction, please do interrupt at any time if you have questions. Don't wait until the end. Wave so that I can see it. So, what are the difference between, in this case, func and lambda? Can you come with some examples? Const expr, yes, not very relevant for this talk, but you're right, yes?
Lambda is referenceable.
Yes, you're absolutely right, and you have understood everything I'm going to talk about in this presentation. The lambda is referenceable. That is the thing. Func can expand to several functions, one for every type t, and you cannot get a pointer to func. You can only get a func pointer to a func of some t, whereas lambda is, as you said, it's one object with several overloaded function call operators, one for every t. And this means that you can take the address of the lambda, and you can pass that lambda to other places that will use them with different t's. That is the essence of what I'm going to talk about today. So since there is no name for the overload set of function templates, or just generally overloaded functions, there is no name for the overload set. But with the lambda, you have that. So let's take an example. It's a bit of a toy example, but we want to check if all numbers in a range are positive. So you write something like this. All of R and the lambda that says return if v is greater than 0. So then we know. And this works. And here you are using a higher order function, whether you think about it or not, because all of takes the range and something that it can call, in this case, the lambda. But it's quite innocent. It's not a high burden on your cognitive system, but it is a little bit noisy, because you will probably write more or less the same thing several times in your code. So what if we do this? I have a greater than that returns a lambda that captures the function argument. So we return something that captures our age for a right-hand argument. And when it's called with something else, an LH, we return the result of the comparison. So I can write the function like returns to ranges all of r or greater than 0. And this kind of code makes it kind of giddy with joy, because it reads almost like you speak about the problem. So greater than 0 here is that lambda where RH has the value 0. Do you follow? So we can also do something more interesting, but more generalized. So we have bind back that was added to the standard library in C++23. What bind back does, it takes something that is callable and something that you want to bind to that callable thing. So you have bind front, you had that since 20 and then 23. So in this case, calling bind back with std greater and t, it means that we will get something back that can, when called, will call std greater with whatever that thing is, which was called with and t on the right-hand side, because it bound the back element. Like so. So this means that when we, in this case, call ranges all of r greater than 0, we call std greater value and the value and 0 that was bound. But, bummer, standard library implementers, we aren't there. We don't have bind back in most standard library implementations. But let's write one. This is very naive, but it works to begin with. We will have a reason to come back to this and make it more sophisticated, but for now this is good enough. Bind back takes something that is callable, f, and it returns a lambda that binds the callable f and the RH right-hand value. We bind it, and when it is called with LH, left-hand side, we call f with that argument LH and the bound value RH. Like so. And then we can do the rest of the comparisons, because they are actually really useful. So you have less than, equal to, not equal to, etc. All right? So let's have a look. And let's see if this actually works. Is this large enough in the back? Can you read this? Excellent, thank you. So we have our naive bind back, we have a greater than, this all positive, and here I'm just calling all positive with a declared get nums. It's difficult to see a lot, but what we can see is that we have this tiny loop here that just compares values. So it's not very noisy code that is generated by this. And in fact, if I change this to I have no idea what shortcut I just pressed. Like that. Okay. And a semicolon. We see that we got we got a result. We can see it returned 1. And if you look carefully, this is main. It really doesn't do a lot. So compilers are awesome, as Matt often says. So let's go for another problem. We have a sequence of numbers, and we want to create a new sequence that is the difference between all of the numbers. That is not an unreasonable thing to want to do, I think. So we can get these values d from the sequence, and we use ranges views pairwise. What pairwise does, it creates a new sequence of neighboring elements, and it passes them on as tuples of references. So you get a tuple of the references to 1 and 3, and to 3 and 8, and to 8 and 2, and to 2 and 3, and 3 and 8, and 8 and 1. Tuples. So we can then call this to transform that takes the tuple, because we know that that is what we get from pairwise. So it must be a tuple. And then we can use structure binding to get the value so that we can write the logic in a way that is actually readable, just compared to using to get 1 from t to get 0 from t. But this construction gets old. It gets old very quickly. At least to me it does. So, can we use std_apply? Are you familiar with std_apply? Std_apply was added to the standard library in C++ 17. It takes a function and a tuple, and it calls that function with each of the elements in the tuple. So it actually does what we want. We have a tuple here, and we have a function. Call the function with the elements of the tuple. How can we get that? So we can write apply. Here's a new syntax from C++ 23 that we can get explicitly named types for our forward references, in this case for the generalized arguments to the Lambda. So now we can know whether f is an L value or an R value. And then we can use this to capture it with perfect forwarding instead of being forced to copy. And you could, of course, do a std forward before you had this convenience in the lambdas, but then you would have to resort to std forward angle brackets decal type of f and angle bracket parentheses f, and it's ugly. This is not ugly. This is good. And then we just call std_apply with f and the perfect forwarding of the tuple. And then we get exactly what we want. So with that, we can write like this instead. Ranges views transform apply auto a, auto b, return b minus a. This is more readable, in my opinion. It's less noise. That is good. Standard library has std minus. Shouldn't we be able to do that? But std minus would return a minus b. That is not what we want. How can we do this? Okay, here's a horrible name. I will get back to that very soon. Swizzle. Swizzle is actually a good horrible name. Swizzle takes a function, and it takes a sequence of indexes. And the intention is that we can, when function is called with its parameters a, b, and c, we can use these indices i's to select in which order we want them to be called. So that I can write Swizzle 2,0,1 of func called with string 3 and nullputter, and it becomes func of nullputter first, because the first argument should be 2, which is the last one, nullputter. The second will become string because it's the 0th argument. And the last one becomes 3 because that is the number 1 argument. And how do we write this abomination? Well, as usual, we capture. We capture the function with perfect forwarding, and this lambda is then called with a bunch of t's. We can create a tuple with the references to t. So the reference collapsing rule says that this tuple will be a tuple of L value references and R value references. We can create this tuple from all the arguments. So now we have an instance of a tuple with references to them. And now we can call f with studget of i's. So i's is these template arguments that we had at the top there to Swizzle. So if it is Swizzle of 2, 0, 1, it will call f with get of 2 from the tuple, get of 0 from the tuple, get of 1 from the tuple. So we get them in the desired order. And that's actually all there is to it. Well, we might want to use concept constraints on the i's. And this is an interesting choice to make and what you want to constrain and not. I choose to constrain that each of the i's in the parameter list must be smaller than the number of parameters that the function is called with. Because if you by accident says, I want argument number 4, and you have 3 arguments in the call, you will get a template compilation error from somewhere deep in the implementation of studget. And there is absolutely not a human person on this earth who is happy about that. You could also add a requirement that f is actually callable with these arguments. And I have made the choice of not doing that, because it hides information. Because if you do that, and you call it with, you get some of the indices wrong, so then you will just get told by the compiler, sorry, I had no way of calling Swizzle of func with this. It doesn't fulfill the constraint that it is callable. Why? Whereas in this, you will actually get failure to call function whatever, because the second argument is a double and it expected a string. Useful information. So constrain enough, but don't constrain too much, because then you lose information. My personal taste. Okay. So we have Swizzle. Yeah, I said I would go back to the name Swizzle. I asked a bunch of people, if I have a function that does this, and I just call it xxxx, that has this behavior, what should I call it? And the usual expected names came up: permutate, rearrange, reorder. And they are kind of descriptive. But if you Google for those in programming, you will find a wide range of very different use cases. If you Google for Swizzle, you will get near 100% relevant hits. So it's a terrible name, but it's a searchable terrible name. So now we can apply your Swizzle 1,0 with stud minus, and I think that is cool.
Why do we need the Swizzle at all if we just say that the first is the first and the second is the second? You don't need to reorder the inputs.
Why do I need Swizzle at all if I just say that the first is the first and the second is the second? I don't think I follow what you mean. Stud minus has its order. It will call them with in the order of the first and the last. So it will call stud minus of 1 and 3, and then of 3 and 8, and then of 8 and 2. So you will get the sign inverted. You will get the negative result of the range. You will not get 3 minus 1, 8 minus 3, 2 minus 8, which is what we want to get. Did that answer your question, or am I completely misunderstanding?
No, okay. Because of the tuple, we put them
Yeah.
in a wrong order.
We get the values from the tuple in the order we don't want them in. So this is the way to turn it around. Yes?
For an example, we wanted to do 3 minus 1 first, then 8 minus 3, right?
Yeah, that is what we want to do in this case.
Otherwise, it will be 1 minus 3.
Yeah.
And 3
Yes.
minus 8. So that's why we want to.
Yes.
Okay.
Correct.
That's the Swizzle.
Yep. Correct. So I consider this a little bit exaggerated, to be perfectly honest, but this is actually useful in a number of situations that are not quite so obvious as these are. All right. So let's actually have a look at this. So we have our apply here, we have our Swizzle, and start with this sequence and the naive first implementation of just the Lambda with deconstruction. And we can see the result, and I'm sorry, I don't. 66 lines, good enough, okay. I don't want to read all of that. But if we use the apply thing with the Lambda with things in the right order, we obviously get the same result, and 66 lines. Okay, so the compiler did the same thing. And if I do this with the magic Swizzle, we again get identical code. Compilers are awesome. They just see through all of this. You're not fooling a compiler that easily. So I work with networking. One thing you often you have to use IP addresses. If you don't know, an IPv4 address is a 32-bit number. It is usually referred to as groups of 4 bytes, hence the first constructor. Sometimes you want to refer to them as just the plain 32-bit integer. So it's useful. We want to be able to compare them. Here we have some new magic. We have 2 pieces of new magic here. From C++20, first of all, if you write just operator equals, the compiler will do operator not equals for you. Noise reduction. Good. And you can add equals default to the end and just say, I don't care, just do the comparison of the members, because that is actually what we want to do. Nice. Saves work. Daniela says it's const expert also, which is even more awesome. Okay. Another thing you need in IP networking is a net mask. A net mask is sort of kind of like an address, but it is used to do bitwise AND with an IP address to see if an address belongs to a subnetwork. An address and a net mask defines a subnetwork. So we want a bitwise operator and between an address and a net mask to get a new address. So I can use something like this, and I can write a function, a higher order function to check if an address belongs to a certain subnet. So you say IP matches of the desired address and the mask, and that defines the subnetwork we want to see if it belongs to. And when called, we see if the bitwise AND between the given address and mask is actually the same as the one actually called with and the mask. Do you see the pattern? Every single slide I have showed you, I have returned a lambda that captures arguments and does something with those captured arguments. That is the talk. Return lambdas that captures, write a function that has arguments, returns a lambda that captures those arguments and does something when called. That's the talk. That's the one thing you should remember from this. So we can use this like std ranges find if address IP matches this 192.168 subnetwork. Cool. You express the code in the language of the problem domain. That is nice. Also, since we make network equipment, we of course need to deal with IP interfaces. You do realize that this is not actual production code. But an IP interface can have a state. Is it on or off? What's its address? What's its net mask? What's its default gateway? And we have some member variables for this. So we can create a higher order function getState by using std memfn. Memfn was added. Added late, but what it does is you give it a pointer to a member function, and if you call it with a reference or a pointer or something pointer-like, like an iterator, it will call that member function of that object. And if the function has more arguments, you will call the returned result from memfn with the type and the rest of the arguments. Which means that in this case, a call of getState on an IP interface object becomes a call to IP interface object.state. Doesn't look very impressive, but trust me, it is. So we add the others. And we also want to be able to set the state. Return to our old friend bind back, because we want to say set state off. And when called with an IP interface, we want to call IP interface dot set state off. Therefore, we use bind back to bind this off in the state variable here. But how can we find an IP interface in a range given an IP address? Find the IP interface that has this address. So, like, if I have a function f1 that takes a y and returns a z, and I have another function f2 that takes an x and returns a y, I want a construction, a composition that, when called with x as an f of x, I get a set z as if called with f1 with the result of f2 of x. So in this case, f2 would be get address of an IP interface to get its IP address, and IP matches with that IP address just returned, and check the result from bool. So how can we make that? Well, okay, you can see from the formatting that some shenanigans are going on here, but bear with me. We can start the easy way first. As usual, we capture the functions as members in a lambda. And when called with a bunch of t's, we call f1 or f2 of t's. This works in a lot of cases. To be a little bit more useful, maybe we should return a state that is decal type auto in case the function actually returns a reference or something. And then we add perfect forwarding for our functions so that we don't unnecessarily copy them if we don't have to. And we get the arguments in the final call as forwarding references and forward them to, again, avoid unnecessary copies. Or in the case of, for example, called with unique putter, avoid a compilation error, it will actually work. And I'm sorry, I have to. I absolutely have to. In functional programming, a family of higher order functions that only deals with composition of other functions is called combinators. Combinators are awesome. There are many well-known combinators, a long list. And you should totally watch Connor Hoekstra's talk, Composition Intuition, from C++ North in Toronto last summer. It's drinking from the fire hose of so many ways of doing functional composition, and compares multiple languages, and he solves very non-trivial problems with them, and you have to watch it 3 times of half speed. And it will be worth it, trust me. But these well-known combinators have names like B, C star, O, F, double star, J, which is, of course, completely impossible to remember. So they have ornithological counterparts. Bluebird, cardinal ones removed. Owl, finch, J, J for letter J. Yeah, I see the combination. I see why. Come on, naming is hard, but this is not trying. This is seriously not trying. This makes me very grumpy. There are several sites like this one that lists all these amazing combinators and what they do, and their letter names and their bird names. The one I wrote is a B combinator. It's called the Bluebird. That thing on the right is actually from that site. I just can't. I'm sorry. I will not write Bluebird in my code. From Wikipedia, in mathematics, functional composition is an operator ring that takes 2 functions, f and g, and produces a higher order function, g ring f, such that h of x is g of f of x. That is exactly what we want. So I'm sticking to compose. I'm sorry. I know a lot of people will be very upset right now, but that's the way it goes. Yes?
Would you be able to remove boilerplate with a unified function call?
Would I be able to remove boilerplate with a unified function call? I don't think I follow. Can you?
Yeah, like basically like the proposal that, I mean, this. Are you familiar with the proposal about the unified function call that basically like you could?
Okay.
And I was thinking like how this could benefit.
The proposal that f.x could be called with f.x of something could be called as x of f comma something. I don't know. I consider that science fiction because it's not here yet. But maybe. So back to compose. When I have this, I can now write subrange find if interfaces, the composition of IP matches and get address. So when this is called with an IP interface, it calls get address, gets the address, passes that on to IP matches, which will tell bool true or false. And of course, we should extract that and give it a name. So with address, with an address and net mask, that returns the exact same composition. So now we can write like this. Range find if interfaces with address. This is human language. This is cool. But what if I want to search with more than one criteria? What if I want to search for addresses that are in a subnet and has a certain state? Both of these criteria. How do I do that? So we have our IP interfaces, and what about a function when all? A higher order function when all. That takes a bunch of functions. And we return a lambda that captures them. This is a cool new C++23 syntax to capture a whole parameter pack. It feels a bit backward to me, but it works. You get used to it. So this capture the parameter pack f's with perfect forwarding. So we can use f's in the function body. So here we return the result of the logical and of calling each of the functions f's with all of the t's. And we get logical short-circuiting with this fold expression. Note that we really, really, really don't want to do perfect forwarding of the t's in the function call. Because if one of the t's is, for example, a unique pointer, and we call the first f's of moving that unique pointer, and it says, yeah, it's true. And then you call the next one with a moved from unique pointer, which is probably not what you want to do. So here, don't do that here. Things will not go well. And now we actually have tools to improve our friend bind back. We can write it such that we do perfect forwarding of the function to call, and we do perfect forwarding of the arguments to bind, and I have now expanded it to be a parameter pack so it can bind multiple arguments. And then we call f of forward of the v's from the direct function call and the captured t's. So now we have a better bind back. We're not quite there yet. I will actually come back to it once more to make it even more generalized. But this is not a bad bind back. So we have our with state. And with that, we can do something really cool now. So we can call loop over all interfaces that we want to activate. Interfaces with a filter when all interfaces that both have the state off and the desired address and mask. And then we just iterate over all those to activate and set their state on. Neat. I'm not going to show a lot here, but what I want to show is that if we look at this activate function, where are we? Here, we see here is the loop from L8 down to here. So step forward 16 bytes, call get state, leave, to do the next one. If it wasn't a match, call address, check if it's the one we want. If it's not, get the next one. Otherwise, call set state on, and then go back to take the first one. So this is quite impressive what the compiler is doing here. How it sees through all these indirections and manages to generate really good code. Yes. Can you say again? I didn't quite hear.
You have an interfaces pipe to filter. Why not just pipe that to transform of set state? I'm not sure why you have a separate.
Why not call to transform of set state? Yes, you can do that. That is perfectly fine. Right. Are you familiar with stud optional? No one has heard of it. Stud optional received some additions in C++ 23. Member functions .and then, .transform, and .or else. Yeah, the last one sounds like a threat, I know. But what it does is, if you have an optional of t and you call .and then, you give it a function as an argument to and then. If the optional actually holds a value, then it will call that function with the t. This function must return an optional of some type I chose U, but it can be the same, but it doesn't have to be the same. So this function that you call can communicate failure by returning an optional that does not have a value. And if the optional of t didn't have a value, then .n then returns an empty optional .u. Transform is extremely similar, but the function that you pass to .transform just returns something. It doesn't have to be an optional, and it will create an optional of that type. So if the function returns a u, then the .transform, if the optional holds a value, then you will get an optional u with the return value from the function. And if it did not hold a value, you will get an empty optional of u. And or else, finally, is, of course, the reverse. If you didn't have a value, you call the function that you passed to or else, and that function must return an optional of t. This is useful in, for example, cache lookup. Get the value for a cache or else create, as an example. Some limitations. T cannot be a reference. There are some people who are working on maybe allowing it. We'll see how that works. But for now, T cannot be a reference. You can fake it by having a T-hosted reference wrapper. It makes the code noisy, but it gets the job done. T cannot be void, which means that since there is no workaround for that, it means that the function that you pass to .transform must return something. It cannot return void. Here's a philosophical question for you. We can talk about that after over a beer. So this means that in this case, our set state cannot be used in .transform, since it's a void function that would create an optional void, whatever that would be. But if we instead return the state type, then it can be used. So a bit of noise here, but find interface that takes a span of interfaces and some predicate, and it returns a reference wrapper to the interface if it finds one, or nothing if it didn't find one. So you see in the last line of the function, it returns to null opt. So we can use this so some hypothetical activate function that takes a span of interfaces and an IP address, and we say, find the interface with address, transform set state on, that is, if we found one, set the state on, otherwise do nothing, and return has value, which will say whether it actually succeeded. It's almost very readable. I don't really like the name .transform, but I mean, I don't like the name transform in this otherwise human readable sentence. Otherwise, it's actually an excellent name. So, this is cool. Let's have a look. So we have our find interface here, which returns this optional reference. And we have this function activate that finds the interface, returns transform if it found it, transformed with set state, and returns true. So what does activate do? Some setup, we have the search loop called get address. If it was found, we call set state and return. Otherwise, we go back this tiny loop where we check the addresses. This is neat. So you don't have to be afraid of code bloat from using these constructions. The compiler is very good at taking care of it. Now for the last problem of this talk. Or actually not problem, last solution of this talk. Deducing this is a new language feature in C++ 23. Have you heard of it? The front row. It's a small feature with a huge impact. There will be lots of conference talks about this feature, I promise you, because it changes a lot. Especially for people who write template libraries. Those of you who don't, you will still benefit because you will get more awesome template libraries to work with. It's currently available in MSVC and in Clang on main if you build from sources. It's not in any released version. It's not available in GCC. And thanks Quarantine for implementing this in Clang. It was actually finished just a couple of weeks ago. And it's amazing. What deducing this does, in essence, is that it allows you to know the qualification of an object that a member function was called in. So normally you write a function, const, non-const, L-value reference, R-value reference, and here you can use deducing this to just see, is it called as an L-value reference, const, or not, etc. And a library companion stood forward like, I will come back to that, but that is a very good companion with deducing this. So, what is deducing this? This is new syntax. This self-ref. Okay. So normally in an object you have this pointer that is implicit. You don't see it in the function call. If you're a Python programmer, you're used to seeing it as the first argument. And this is essentially the Python way of doing this. But here it's templated so that we can get the perfect forwarding and get the type deduction. So I can actually write something like this. So on the first test here, check if it is const if we remove all the ampersands. And then if so, we write const on standard out. And then we can check if it is an L-value reference, write 1 ampersand, and otherwise write 2 ampersands to see that it is. So we have this f now. F is this lambda. And if I'm calling this, as in the first line here, with the value, it writes ampersand. Because f is not const, and it's an L value. If we call it through as const, so we cast it to a const ref, that is what we see, const and 1 ampersand. If we call it via std move to cast it to an R value, we actually get ref. And unsurprisingly, we get this not particularly useful const ref thing. But how would I have written this code if there wasn't this deducing this functionality? I would have to write a class, and I would write 4 function call operators. One that is L value const, one that is R value const, one that is L value non-const, one that is R value non-const, and do each of these outputs in each of them. So possible to do the same thing, but a lot more work, and not possible at all to do in a Lambda. So, final fix to bind back. We use deducing this to get this self-ref so that we know if the bound back thing is called as an R value or not. That is the primary important thing, but also if it's const or non-const. And we use this forward like. So we say that, yeah, the bound variable f, if self that is an R value, then we want to move f. If it is an L value, we want to pass f as an L value, or you call f as an L value. Forwarding of the v's are exactly as usual, but also the same with forward of the captured t's. And this changes something, because this means that the bound back object can now work with bound back move only types in a safe way. Because if you call this bound back thing that has bound unique pointers, you need to make sure that you have an R value. You just did move it or something, which make it visible in the code that this object is now disappearing. Do not trust it to do anything useful after this. And then it will move the unique pointer, which is what you want. Yes?
So inside the inner lambda, f is a constant.
Why are...
Make the lambda mutable so I can actually move it.
Okay, so the question is, inside this inner lambda, f is a constant. No, it is not a constant. This is... If... So to begin with, in lambdas, the capture itself is never const. It's a function call operator that is const, unless you write mutable. Here is a templated way to express mutable, const, L value, R value as one thing. So this does not do some evil cast away const. It does not. This is safe. It works with the category of the type. So as I said, now with this, it can actually be used in a type-safe way with things like unique pointer. So I will show it to you. So we have a simple thing here now, bind back something that is passed things by value as pointers, and we just return, we just add them. They add the result of dereferencing them. And we bind back a unique pointer. And this works because I stood move f on the call. So now f is dying. We are signaling that f is going, which means that you may move the captured unique pointer. If I do this instead, we get an error. Call to implicitly deleted copy constructor of stood unique pointer in forward like self of t's. Before this, you could sort of kind of handle unique pointers by making your lambdas mutable, but then it was hidden that you lost your inner values, that you lost your captured values, and that is dangerous. With deducing this, you get code that is more honest and says what it does. If the function object that you have, the return result from bind back, if that is about to die, then why not move away its contents? Otherwise, you don't at all. So you can trust that the right thing happens. Going back to the opening slide. I am not talking about food. In mathematics and computer science, currying is the technique of translating the evaluation of a function that takes multiple arguments into a sequence of functions, each taking a single argument. This is named after a guy called Haskell Curry. So what this means is if you have a function f, a curried function f that takes a, b, c, and you call it with only one argument, you get something back that is callable with 2 arguments, and it has bound the first one that you called it with. So you can choose to call them with all 3. You can call it with just the first, and then you have something that is callable with 2. That itself is curried, so you can call it with only 1 and get something back that is callable with 1 argument. I like my code formatting setup. It's really good. So we see a new use of deducing this here in the first case. You do realize that these spaces will be filled with a lot of ampersands and angle brackets, right? But we start simple. This one actually works. So we capture the lambda itself as a reference. We're not interested at all in this case in whether it's an R value or L value or const or not. We just want to have it as a name so that we can call it recursively. Calling lambdas recursively until now has been kind of awkward. Not impossible, but it takes some gymnastics. But in this case, it's easy. Just capture itself as a reference with deducing this. So then we can check first if called with a bunch of t's, can the function be called with those t's? Have you seen this use of if const exponent requires before? By the way, it's kind of neat. So this is how you can write a compile time check if a function can be called. If const exponent requires, if the function cannot be called with that, then requires will be false, so we will not execute that. So if it does, then we call f with those t's. Otherwise, we recursively call curry on bind front of the function that we captured and those arguments that we were called with. So we have a recursive definition here. And now some more ampersands, because why not? So we get the category of the inner lambda if it's R value, L value, const, non-const. And we use this forward like to it so that we can see if this was an R value, we cast f to an R value when we do the call. And likewise in the recursive case, we move f if we can, if the function if this lambda is in fact an R value. And finally, we do, of course, do perfect forwarding of all the t's. And this is how you implement curry. And this is my last demo. So I have curry here. It's a bit noisy, I know, but I'm lazy. I have an MK here, make, that takes something and returns a unique pointer to that type, just so to reduce my typing. And I curry, f is a curried function that takes a, b, c by value. We assume that they are pointers. We return, we print the dereferenced pointers values and return the sum of the dereferenced pointers. And now we call them. The first call is f of all 3 values, and it prints 1, 2, 3. We call f of, can maybe change like this, call f with two arguments, and then call the result of that call with 1. Or here we call it with 1 argument and call the result of that with 2 arguments. And the last one returns each of these individually. Call f of make 1, call the result of that with make 2, call the result of that with make 3. But the really amazing thing, in my opinion, is this. If I don't do the print, That is awesome. No memory allocations, no functions calls, no nothing. It just says, okay, the first 3 ones are ignored, so who cares? And the last one, yeah, the sum is 6. Return 6. Done. Hug a compiler writer when you meet them. So, to summarize here, higher order functions in general and function composition in particular is extraordinarily powerful. You combine different ways of passing information. And some of the new things in the standard library, like ranges and optional T, and are you familiar with expected T and E? Expected is like optional, except that if you don't get a value, you get an excuse. That is what E stands for, excuse. And new language features like the variadic lambda capture just makes life easier. You don't have to do this roundabout way with capturing values in tuples. Just write with a bit awkward syntax, but still, just write. Capture this parameter pack. And using this is a new superpower. It will change things. And everything I showed today is things that you could do before, but with a lot more verbose code, like writing a lot of overloads. But there are actually things that cannot be done today that will be solved with deducing this. I recommend that you read Cy Brand's blog post about deducing this. Cy was very involved in the standardization of this function. And this blog post go through briefly what it is and a number of use cases shown by example where it makes it easier to do things. And the very last example actually shows something actually from std-optional, the extension to std-optional, that is not possible at all to do within the language without deducing this. And with that, I say thank you very much for your kind attention. Here's how you can spam me if that is your thing. Questions, observations, tomatoes? Yes, Daniela.
Daniela, wait for the mic. Yeah.
Thank you for this great talk. An observation. You're using a lot of lambda expressions, and that don't actually capture anything, but give the closure types a name. It's just the same as a function, right? Is there a reason why you're doing that?
Is there a reason why I'm doing that? There is a reason. In almost all of those cases, these lambdas take arguments of arbitrary types. So they are, in essence, function templates, which you cannot pass to some other higher order function because you don't have a thing if it is a function. But if it is a lambda, you can pass the lambda with its overload set of function call operators.
Just wanted to make it clear.
Others?
What impact does using a lot of lambdas, and especially your examples at the end, like carrying, have on the compiling performance?
That is an excellent question. The impact on the compilation performance. The honest answer I can give is that I have not suffered from it, but as you saw in these examples, the compiler sees through all these abstractions, and the seeing through process obviously takes time to do. So there is a compilation time cost. I personally haven't suffered from it, but I may have been lucky, I don't know.
So I definitely do love the resulting code. But what if somebody does something wrong and there's a compilation error? How do you handle these?
Write correct code. No, but this can be a problem, and that is actually one of the reasons I brought up this example. If you remember Swizzle, where I showed the constraint on with a requires clause, that I said it's bad to constrain it fully. Well, maybe not bad, but it has the effect that it anonymizes what the problem is. It hides it, where it can be actually better to expose what the problem is. I don't really honestly remember having had much problems understanding what is happening, because usually what happens is that you have captured some move-only type and you get a compilation error saying that you're trying to invoke the copy constructor of unique pointer. What are you doing? And yeah, there can be some head scratching and wonder, where does this copy come from? Why is it copied? But usually you find somewhere where that, I should have used a move here. But occasionally there may be problems. I don't know. Maybe I've been lucky. I don't know. All right. Thank you all.